Okay, let's jump in and sorry for being late today. I had problems with the printer. So Audra's not here today, and the printer's on black toner. So our worksheet I had to scramble to print it. It's printing upstairs right now, so hopefully we'll have that. Hopefully we'll have that ready for here after class. So we're talking about net ionic equations. We dealt with this a little bit in lab yesterday. We also talked about precipitates. So the quicker you get through your precipitates, the better off you're going to be. And it's kind of the main precipitates are the ones that we're going to talk about, not the complete list, which is actually very, very complex because there's partial solubility, there's complete solubility, there's just very different levels of solubility with these things. But again, for our class as a general chemistry course, the table that you have, this table here, is the one that I'm going to hold you accountable for understanding precipitates. So again, we walked through this on Monday, so this is the table that you should be working on putting memory to, and I hopefully I helped you with a little bit on how it's not just brute memory, but there is some work to understand which of these are soluble, which of these are insoluble. Now, in lab yesterday we talked about this thing called the net ionic equation. When you're writing a net ionic equation, you do have to understand that if a compound is one of the exceptions of insolubility, it's going to become a solid. And we saw that yesterday with our white precipitate from silver chloride and our potassium chloride that we made from decomposition of potassium chlorate. So this was the reaction that we would have seen in lab. And what you can see here, yeah, we had a little bit of nitric acid in it. That just gets the ball rolling, so that's not in this particular equation. But whatever's on the left of the arrow, if it's still an aqueous on the right side of the arrow, then we cancel it out. Potassium is aqueous on both sides of the arrow, so we cancel it out. So our net ionic equation, this is going to be a silver fighting a chlorine going to a solid, or a silver chloride solid. Okay, so this is the type of thing that we want to be working through, getting rid of the spectator ions, telling what the actual reaction is. So if I gave you a question on exam 2 or on a quiz that said something like barium chloride plus potassium sulfate goes to what? So what I want to do is I want to first off decide what is barium chloride. Well, I know from the periodic table that barium is a 2+, so barium chloride is going to be BaCl2. Okay, so that's barium chloride. Again, that should be pretty straightforward from where we're working with nomenclature. I also know that potassium sulfate is SO3 or SO4. Oh, it's the second one down, so it's SO4, and it's 1 over, so it's 2-. So sulfate is SO4, 2-. Potassium is K single plus, so potassium sulfate looks like that. Now what I want to ask myself the question is, are either of those within the exceptions of my solubility rules? So if you go back up to your solubility rules and you ask yourself, let's see, chloride. Chloride is always soluble. Chloride is always soluble unless it's with silver, mercury, or lead. Oh, well that's soluble then. So that tells me this is aqueous. Okay? Then I look at my potassium sulfate and I say, okay, potassium sulfate is always soluble except with strontium, barium, mercury, or lead. Oh, it's got potassium. I also know that there are no exceptions to the alkali metals. There's an alkali metal, so therefore I know this is soluble. So this is potassium sulfate, AQ. Does that make sense? I use my solubility rules to know that's what that looks like. Therefore, barium in water is 100% Ba2+ plus chloride minus plus potassium plus, and you could balance the chemical equation if you want. I'm just showing you the spectator ion. Plus sulfate 2-. There you go. There's what's going on. On this side of the equation, then what happens? Well, when potassium finds chlorine, it's all hunky-dory. When barium finds chlorine, we just go back to that. But what happens when barium finds sulfate? Is barium sulfate one of the exceptions? It is. Sulfate is always soluble, again, always soluble unless it's with barium. then it becomes insoluble. So that means that when barium sees sulfate, we end up with BaSO4, and we end up with potassium plus and chloride minus. Okay? So this then is a solid, it's a precipitate. So when I cancel out my spectator ions from the left and the right, notice the net ionic equation is simply barium finding sulfate, go to barium sulfate. Okay? But the only way I'm going to know the net ionic equation is if I have some idea of solubility and insolubility on this table. Okay? So this is the way we work these, and this is, again, this is a nice overview of some of the common anions and their solubility profiles. Okay? So that's dealing with net ionic equations. Again, we saw that in lab yesterday, and I would expect that to be fairly straightforward in coming up with the net ionic equation of certain reactions. Okay? Good? Now, we're going to talk about acids and bases in here quite a bit, especially when we get into some titration reactions here on Friday and Monday. Or actually on Wednesday, I guess, because we're not in class on Friday. There are 3 definitions of acids and bases, and you need to know them, and you need to know why they're different. They're all important. The Arrhenius definition is the most simple. It's the simplest. It's one of the oldest, and it simply deals with water. And that's we're gonna see that we derive the pH scale from the Arrhenius equation, okay, or the Arrhenius idea of acids and bases. Bronsted-Lowry is a different definition. We use that when it's different. We have to know it because that's where we get what we call our Ka or our pKa tables. pKa understanding is the most important for organic chemistry, as is the Lewis definition of acids and bases, but we'll get to that a little bit later. For now, we're going to stick with the Arrhenius acid definition and base definition and the Bronsted-Lowry acid definition and base definition. So Arrhenius basically defines an acid as something that increases the amount of proton in the solution. Proton is H+. Some people call it hydronium. I call it proton because that's what it is. Remember, hydrogen, not deuterium or tritium, but hydrogen, if it's lost its electron, is simply a proton. There's no neutron in hydrogen. Hydrogen has an element up there, well, it's H2, it's diatomic, but it has a neutron, a proton, and an electron. If I remove the electron, it simply is a proton. So that's why we oftentimes just call H+ a proton. Especially in organic chemistry, that's what we call it. In general chemistry, we oftentimes will call it a hydronium, but it's a hydronium cation or ion. Okay? So Arrhenius definition of an acid is anything that increases the proton or the hydronium concentration. That's what an acid is by definition. All right? Bronsted-Lowry is a little bit different. Bronsted-Lowry defined them as a proton donor. Okay? Notice it's a slightly different. Both dealing with proton, H+. Arrhenius said anything that increases the concentration of proton. And that's where, again, we're going to talk about pH. That's what P, the log scale of the H proton concentration, comes from. But with this definition is anything that actually donates a proton or an H+. Okay? You see they're similar, they're related, but there is a slight nuance between them. On the other hand, base is quite different in the way they define them. Arrhenius, and again, this is review, but 1, 2, 3, 4, 5, 6, 7. These are the 7 that we need to know. If you want your whole complete table of all 8, right down here, periodate acid is also a strong acid. But I'm not holding you accountable for that one. You need to know perchloric, chloric, sulfuric, nitric, hydroiodic, hydrobromic, and hydrochloric. Those are the 7 strong acids for our class. Okay? The complete picture is there are 8 of them, and those are the 8. There are 8 bases, and there are 8 acids. Okay? So again, we memorize those. You remember the 8 strong bases? Yep, that's all it does, right? It's pretty simple. Boom, boom, boom. They're all hydroxides. Okay? The hydroxides of those 8 are all strong bases. And what do we mean by strong? 100% disassociation. That's what that means. Okay, strong is directly related to 100%. Okay, complete disassociation. Now, Arrhenius definition of a base is anything that increases the concentration of OH-, the hydroxide anion. Okay, Notice Arrhenius' definition of an acid: anything that increases the proton concentration. A base is anything that increases the hydroxide concentration. So that's what we're dealing with pH and pOH when we get there. Bronsted-Lowry is a little bit different. Anything that accepts a proton is a base. Anything that accepts a proton is a base. So Bronsted-Lowry is dealing with a proton. Anything that produces a proton is an acid. Anything that accepts a proton is a base. Okay? Whereas Arrhenius deals with the concentrations of proton and hydroxide. Notice Bronsted-Lowry does not deal with hydroxide. That's an Arrhenius definition. Bronsted-Lowry deals with anything that accepts that proton is by definition a base. Okay? Now, I will just say this verbally because it's not in the notes, because you're not held accountable for it. The third definition is what we call the Lewis base and the Lewis acid. It is the broadest definition of acids and bases. A Lewis base is anything that donates a pair of electrons. That's really important, especially when we get into organic chemistry. We're going to see that electrons always go. Positive charges don't go. Electrons go. And here's why. Electrons are something. When they're missing, the vacuum, the void, is just positive. Okay? Think of it this way. We've talked about this. We don't quantify dark. Dark is a byproduct of no photons. We quantify light. We don't quantify dark. Okay? Same with heat. We quantify heat. We do not quantify cold, even though we say it's cold. Heat is something. It's the motion of something. The absence of it is what we call cold. And I would make a real argument for this exact same with sin. Sin is the absence of the presence of Jesus in that moment. Okay? He is there. That's life. His absence is death or sin. Okay? Very, very important, and we see that all through science. Likewise, electrons are something. Electrons go. Okay? You can't have coldness going somewhere. You can't have darkness going somewhere because there's nothing there. Again, darkness is the absence of something. Cold is the absence of something. A positive charge is the absence of something. What's it the absence of? The electron. Okay? So it's the electrons that go. Electrons are always the one that go. So it's one of my pet peeves, to be honest with you, which is why this is completely wrong. Real pet peeve of mine, because I have to unteach this in order for us to really understand organic chemistry. This graphic is wrong. Does anybody want to take a stab at why this graphic is wrong? What did I just say? Electrons always go. All right? You can even say that's Einstein's axiom number 1 of chemistry, because that's what I will drill into organic chemistry. Electrons always go. Electrons always go. Electrons always go. So Lewis base is a pair of electrons. Yeah, Hunter, want to take a stab at it?
So it was like the ammonia donating to electrons?
The ammonia is who has the electrons. So this graphic is completely wrong. It should be an arrow from the lone pair on ammonia attacking the proton. You see how it's completely backwards? This graphic has the hydrogen going. What did I just say? Electrons always go. Hydrogens don't go. Hydrogens are attacked. Okay, so this graphic, if it were going to be correct, should look like this. And we'll get to this when we get to Lewis dot structures. But for now, you might not know that or some of you that had chemistry, like Hunter, and some of you others that have had chemistry before, you'll know that your Lewis dot structure of ammonia should be nitrogen with a big lone pair of electrons, and its hydrogens often a tetrahedron or an sp3 hybridized orbital set. That's where we're headed with our Vesper. But with that, as I add that to my water, those are my Lewis dot structures for ammonia and water. This graphic has this going here. That's wrong. Electrons always go. These electrons go to that hydrogen, taking those electrons back on. That in turn gives us what we are going to call our conjugate acid conjugate base pair. And it looks like this, plus the hydroxide now, which has this, okay? So that's the correct version of that, but notice, by definition, electron pair going to a hydrogen, or proton in this case, is a base. So a Lewis base is an electron pair donor, a Lewis acid is an electron pair acceptor. Arrhenius definition, well, we can't even use Arrhenius here because we don't have the hydroxide except over here, all right? So you can see how we're going to need to use these three definitions, the Arrhenius, the Bronsted-Lowry, and the Lewis, to really get an understanding of base-acid reaction, okay? Bases are the electrons. Bases have the electrons, so electrons always go. Bases attack acids. Acids don't attack bases, okay? It's just one of those things to keep in mind as we're working through this understanding of our general chemistry, okay? So in this reaction, what actually happens is the electrons on my sodium hydroxide, again, the electrons always go, the hydroxide has the electrons. So the electrons that are here on my hydroxide are going to say, hey, wait a minute, I see a proton right here that I can go attack. So this hydroxyl group goes over, grabs the hydrogen. Those electrons, they say, oh, cool, I've got this negative charge. I'll go grab the sodium. So you get the sodium acetate version of the acetic acid, and you generate water. Okay? So this is what we would call well, this is a combination reaction. It's not a neutralization reaction. A neutralization reaction happens with strong acid, strong base. This is a weak acid, strong base, but we'll get into that later. So what happens with this is we have a strong base attacking a weak acid. The electrons here go over, grab the proton. Those electrons then say, okay, I'll grab the sodium, and so we get this reaction that takes place. Okay? Now, when we have a strong acid and a strong base, that is a neutralization reaction. This right here is not neutralization. This would actually end up slightly more basic. It would not be 7.0 like a strong acid, strong base. And you'll get to that with Dr. Harris, not with me, unfortunately. Okay, so if I have a strong acid reacting with a strong base, notice strong acid, strong base, by definition, I've memorized those. The electrons here on the oxygen then go attack the proton. Then the electrons off the chlorine come over and grab sodium, and we get sodium chloride. So we get a salt and water. So this is what we call a neutralization reaction. If it's a strong acid and a strong base, it goes to 7.0. It's a neutralization, or neutral. Again, we're not going to deal with the pH scale this semester. That is next semester. Super fun stuff. You'll get into that with Dr. Harris. Okay? Overall, what's the net ionic equation? Well, it's a hydrogen and a hydroxyl group going to water. That's the net ionic equation in this reaction. Okay? Now, sometimes in these reactions, like we saw in lab last week, not yesterday, but the week before, we get these compounds out that decompose. So there's two of them that you need to know. There's several, but for us, again, general chemistry, the two most common are the ones that we're going to learn. So those are carbonic acid, which we've already seen. Carbonic acid gives off carbon dioxide and water. It's not stable, so it decomposes to water and carbon dioxide. Again, we utilized that last week in lab. And so what happens if I take something like calcium carbonate with hydrochloric acid, we get calcium chloride out plus carbon dioxide and water. Okay? It forms carbonic acid, which decomposes to carbon dioxide and water. All right, so these are what we call gas-forming reactions. So any reaction sequence that you see, there's two of them that we need to know. If you see carbonic acid generated, okay, just like in lab, if you see this compound in our reaction, this is not stable. So we put it in brackets. It decomposes to water and carbon dioxide. Okay, that's very important. It's not stable, so it's a decomposition. The other one like this, there are two, like I said, there are two, deals with, again, this is the carbonate and the bicarbonate. So you can see that both these reactions here, if I take sodium bicarbonate and hit it with HBr, I also get out carbonic acid. Carbonic acid comes from the carbonate and the hydrogen. The carbonate and the hydrogen. That's what carbonic acid comes from. The second one that you need to know specifically deals with the sulfite, not sulfate, but sulfite. If I generate sulfite, sulfite also generates hydrogen sulfite. Okay? So H2SO2. And you can see that there, SO2, oh, excuse me, SO3, not 2, SO3, okay? Hydrogen sulfite, or sulfurous acid, not sulfuric acid, sulfurous acid, also decomposes, and you can see it up here, to H2O plus SO2, okay? And it actually really is a smelly reaction. This would be rare for us to actually see this in the laboratory setting. SO2 is not a super healthy one to have in your lungs, so we typically don't do reactions that generate this, but those are the two real common gas-forming reactions, okay? So again, sulfur dioxide and water, if it's sulfurous, acid is generated. Remember, ite goes to us acid. Ate goes to ic acid. So sulfurous acid is not stable, just like carbonic acid is not stable. So those are your two that generate gases, okay? That's it, just two. For us, yeah, there's more, but those are the two main ones that we see in the laboratory setting. Now, this is where it gets a little bit fun. We're gonna talk about oxidation reduction. Okay? We can't have chemistry without oxidation reduction, right? The way I've always memorized this, even from when I was a junior in high school, at Shasta High School in Redding, California, oxy-loss. Oxy-loss. Just walk around campus saying oxy-loss. Oxidation is loss of electrons. Oxidation is loss of electrons. So if I am a sodium atom and I have 11 electrons, if I am a sodium atom and I have 11 electrons, and I lose an electron to become sodium plus, have I been oxidized or reduced? Because oxidation is loss of electrons. It's lost one electron, oxy-loss. Therefore, when sodium goes from metal to sodium cation, it has been oxidized. It has undergone oxidation. But here's the cool thing. If I'm moving electrons around, someone has to gain them. You can't just have spontaneous electrons kicked off of sodium and buzzing around out there. Or at least on Earth. Out there in the plasma field, that's a little different. But here, you can't just have a random electron just move off of an atom unless something has gained it. So, if there's been oxidation, there's also been reduction. So if I've lost one electron, somebody's gained one electron. If I've lost 2 electrons, someone has gained 2 electrons. So oxidation is loss of electrons, reduction is gaining of electrons. Okay? So oxy-loss starts with oxidation. Oxidation is the losing of electrons. So watch what happens here with this example of calcium being oxidized. Calcium metal. Super happy metal, has all its electrons, 1s2, 2s2, 2p6, 1s2, 2s2, 2p6. Actually, it's going to be 3s2, 3p6, and then 4s2. Okay, we'll get to that. So it's going to have all of its electrons. As soon as the big mean oxygen is in its presence, oxygen says, wait a minute. I'm the second most aggressive element on the periodic table. How do I know that? Electron yes, nailed it. Electronegativity, okay? Fluorine, 4.0. Ooh. What's oxygen? And what's nitrogen? And what's carbon? And what's boron? And what's beryllium? And what's lithium? What's chlorine? Sulfur? Down by 0.5. 2.5, down by 0.4. 2.1, down. 1.8. 1.5. 2. Bam. See? And arbitrarily assigned hydrogen. 2.1. Good. So, oxygen, being the second most aggressive element on the periodic table, says calcium, if you've got 2 electrons in your valence shell, I'm grabbing them. I'm taking them from you because I want them. So what has happened to calcium? It's been oxidized or reduced? Why has it been oxidized? Because it lost 2 electrons, and oxidation is loss of electrons. What then has happened to oxygen? Oxygen's been reduced. It's gained 2 electrons. Huh, isn't that cool? So in a reaction like this, when I have 2 elemental compounds, calcium in its elemental form, oxygen in its elemental form, remember it's diatomic, always O2. Not always, but it also is O3 and ozone, but we'll get to that. It's an allotrope. So when we have calcium and oxygen in their elemental forms, calcium has 2 extra electrons to look noble. Oxygen says, man, I'm grabbing those because I am the second most greedy element on the periodic table. I'm grabbing them. What happens in this is we get calcium 2 plus oxygen 2 minus, calcium oxide. Isn't that kind of cool? So in this, calcium's been oxidized, oxygen has been reduced. Calcium lost electrons, oxygen gained electrons. Oxy-redox reactions are oxidation, reduction in conjunction. Okay? Questions on that? So, elemental, now I'm in an ionic compound. Okay? And I could tell how ionic I am by knowing the difference in electronegativity between calcium and oxygen. So calcium is going to be around 1. You don't have to memorize. I didn't have you memorize the third row down, but it's going to be around 1. And the only, by the way, the only noble gas that has electronegativity is xenon, and it's 2.8. But we'll save that for a rainy day, or a snowy day in this case. So with this oxidation reduction process is a really important thing. And I always say, start with oxy loss. Therefore, reduction is gain. Okay? Oxy loss, right? That's really important. One can occur without the other. So if something's been oxidized, something's been reduced. Now, here's where we're headed with this. We need to be able to calculate the charges, the formal charge on a molecule. All right? So this is where we're going to head. With oxidation reduction, we have to also know that certain metals will oxidize other metals. This is kind of weird. This is actually how you get silver plating. You can actually put silver on metal if you have another metal on there. Silver is pretty aggressive, so it will steal someone else's electrons. So there's what we call the activity series. I'm not going to have you memorize the activity series, but you do need to have an idea of the activity series, all right? So if I put something like magnesium and hydrochloric acid together, in this reaction, magnesium is going to lose electrons because that's what metals do. So metals are typically oxidized. So magnesium sits over here and it says, if I lose 2 electrons, I look noble, I look like neon. So I'm going to prefer to lose my electrons. So if I put magnesium in the presence of hydrochloric acid, hydrogen, who's lost its electron to chlorine, says, oh wow, I've got something weaker in here than chlorine. Chlorine doesn't want to give up an electron. Remember, chlorine's 3.0. Magnesium's over here, remember 1.2, okay? So chlorine's not giving up its electron. So hydrogens float around out there saying, well, crud. I've got chlorine who says no, but magnesium says yes. Sweet. So magnesium, I'm taking those electrons. So hydrogen, H+, says, okay, magnesium, I'm going to grab your electrons, and I'm going to go back to being elemental. I'm going to be happy again. So magnesium's been oxidized, hydrogen has been reduced. Okay? Again, there's an electron transfer. Oxidation loss, magnesium's lost its electrons, hydrogen's gained it, so hydrogen's been reduced. And we see that here. HCl plus magnesium goes to hydrogen in its elemental form, which is always a 0 charge, plus magnesium chloride. Okay, isn't that kind of cool? So we're seeing these electron movements in this process of oxidation. All right? This is the way silver plating takes place. You could take, and you can do this in lab, you could take a copper wire, you could put it in a solution of silver nitrate, the same silver nitrate that we had in lab yesterday. You just put a piece of shiny, has to be shiny copper, can't be oxidized copper. Shiny copper in that silver nitrate solution, come back in a couple days, and it'll have silver coated on the copper rod, and it looks like this. And that's because silver and copper have different oxidation levels. One wants electrons more than the other. Notice, silver here is Ag+. Silver here becomes Ag metal. So has silver undergone oxidation or reduction? What
is oxidation? Loss of electrons. Has silver lost or gained electrons? It's gained electrons, hasn't it? Over here, it was Ag plus. Over here, it's Ag 0, not plus, meaning it has its electron. So silver gained an electron. So it has been reduced. Oxidation is lost. So who in this scheme has been oxidized? Copper. Yeah. Copper here was a metal. Copper here is Cu2 plus. Yes. Is it 2? Is there 2 there? Yeah. Cu2 plus. Copper can either be 2 or 1. Okay. So this is what we talk about with certain metals undergoing oxidation in the presence of other metals. So how do we know who oxidizes who? Oh, we memorize a table. Isn't that fun? And the table looks something like this.
Oh, what?
I know, another table that we get to memorize. Yay! No, you don't have to memorize this table, but you do need to understand who's where. That's important. Notice the ones that are all down here. Anybody want to take a stab at those guys? What's special about all of those? Where do we know those from? Where have we seen silver and gold and copper? Now the periodic table, but where in the real world? Jewelry, right? Ancient, copper. Copper. If you look, it's actually interesting. If you look at metallurgy and the technology, it's basically when the next people group made the next best metal, they became the more powerful nation, right? It's like we're going to be out there swinging lead swords around. That doesn't really get you very far, right? But if you had like a stainless steel or a bronze or Bronze Age, right? The Copper Age, you're seeing those down here. Copper, silver, gold, platinum. All these precious metals don't like to be corroded, okay? So in the presence of something softer, they're going to steal electrons. They prefer to have their electrons, okay? So anything down here prefers to have its electrons, meaning anything up here is going to prefer to be oxidized. Oxidation is loss of electrons. As I get softer and softer and softer, I'm going to prefer to be oxidized. So anything over here is going to be oxidized by anything over here. Okay, that's a general rule that you should see. You'll see that on an exam or quiz. I'm not going to have you memorize this, but if I do put silver and sodium together, you better tell me which one oxidizes who. Okay, that is important to understand the trend there, not a memorization thing. I wouldn't do something brutal like give you aluminum and manganese. That'd be kind of me to have to memorize a chart to get that one correct, right? Oh, manganese and aluminum, they're right next to each other. Or magnesium, that'd be a great one. I'll give you all three. Who oxidizes who? No. But I will give you one of the alkali earth metals or the alkali metal in the presence of one of the precious metals. That to me would be a fair understanding of what's going on here. Who wants the electrons? Make sense? Yeah. Okay. We were going to do a worksheet today. We have about 10 minutes left. Why don't I explain what we're going to do on Friday then? Because Friday is going to be a work day. We've got a worksheet that we're going to work through oxidation numbers, and we're going to work on some of this stuff on that worksheet, but it's being printed. I was going to leave it for today, but why don't I spend the last 5 minutes on explaining how we calculate oxidation numbers. If you would, I know this is like the last 2 days have been long lectures. I get that, but we do have some ground that we just have to get through and slog through a little bit. What we're going to go through next is not super straightforward, so you got to stay with me. I'm going to try to explain this as easy as I can, but then on Friday it's going to be a work day. You're going to work this out because this is really important to be able to calculate oxidation charges and oxidation states of particular atoms and elements, okay? So oxidation numbers. We need to understand who's being oxidized and how they've been oxidized, okay? So with this, we need to have a few rules of oxidation. Now, where I think this is fascinating, at least in the real world, is something that we all know. We just probably never been taught this in the context of oxidation. So if I take, I wish I had a different color pen. If I take something like methane, or as the British call it, methane. If I take methane, I know methane burns. Methane, ethane, propane, butane, isobutane, hexane, heptane, octane, all those that we look through. And I take methane and I convert it to methyl alcohol. And I take methyl alcohol and I convert it to formaldehyde. And I take formaldehyde and I convert it to formic acid. And I take formic acid and I convert it to carbon dioxide. You don't like the squeak? You like the squeak?
No, my ankle's small.
Oh, nice, nice. So notice what's happening here. This carbon is what we want to be paying attention to. Okay? Something's happening to this carbon. This carbon is having progressively more oxygen added to it and hydrogen taken away from it. So think of the word oxidation. What does that word sound like? Sounds like oxygen, right? Oxidation sounds a lot like oxygen because that's where it comes from. Oxidation. So oxidation is the loss of electrons, oxyloss, and it's also the gaining. Okay? It's also gaining oxygen. Okay? So oxidation, more oxygen. Oh, that's kind of cool. And or less hydrogen. Okay? So oxidation is more oxygen and or less hydrogen. So stay with me, because that's where we're going to head by calculating our formal charges. How many hydrogens on this carbon? 4. How many hydrogens on this carbon? Oh, we lost one, didn't we? How many oxygens on this carbon? How many oxygens on this carbon? None. So this carbon has lost a hydrogen and gained an oxygen. What is oxidation? More oxygen and or less hydrogen. In this case, it's both. So this carbon has undergone oxidation. That's how we abbreviate that. It's been oxidized. Right? So when carbon goes from methyl alcohol to formaldehyde, how many hydrogens are on this carbon? How many hydrogens were on this carbon? So what did it do? It lost a hydrogen, and oxidation is, loss of a hydrogen. So this has undergone oxidation. So over here, how many hydrogens are on that carbon? 1, right there. And it has 2 oxygens on it. Oh, so wait a minute. It had 1 oxygen, 2 hydrogen. Now it has 2 oxygens, 1 hydrogen, so it's undergone oxidation. And by the time I get to carbon dioxide, notice that hydrogen is gone, so it has undergone oxidation. So this is what we call living carbon, and this is what we call dead carbon. And it's dead because it's lost its electrons. It no longer has the ability to move its electrons. It's completely dead. And we have to wait for a certain special process called photosynthesis, you got it, to go back from dead carbon back to, and it doesn't go all the way to methane, it goes to living carbon, it goes to here, it goes to the cellulose, okay? So, this process then, it's important for us to be able to calculate what is the oxidation state of carbon. Here, what is the oxidation state of carbon? Here. I know it's undergone oxidation because it's gained oxygen and or lost hydrogen, but how can I know that for sure? And that's what we're going to work through in the last 5 minutes of class. So oxidation is my oxidation number. What is the oxidation number of my carbon in this sequence from methane all the way to carbon dioxide? Well, I'm glad you asked. Any element in its elemental form is always 0. So hydrogen as H2 is 0. Oxygen as O2 is 0. Aluminum as a metal is 0. Calcium as a metal is 0. Anything in its elemental form is always 0. Okay, number 1. Oxidation number is the same as my cation or my anion number. Okay? If I'm a simple cation of calcium 2 plus, my oxidation is 2. All right? 2 plus or 2 minus, etc. So the oxidation number of monoatomic ion is the same as the ionic charge. Notice, monoatomic, not polyatomic, monoatomic. So sulfide, nitride, oxide, chloride, sodium cation, potassium cation, calcium cation, iron cation, all of those, whatever the charge is as its cation or anion is its oxidation number. That's very simple. It's just what the oxidation number is, okay? Now, this is where it gets a little bit dicey. Non-metals have to be calculated. Non-metals, I can't just look at the non-metals and go, oh, that's what it is, because non-metals get a little bit more tricky, and so here's what we have to do. Non-metals, we have to actually know a few rules, and we have to learn these as what we're working with on Friday. So let's go through these. Oxygen is typically -2. The exception to that is if it's a peroxide. So something that looks like this, so water, if it's water, oxygen in water, like this oxygen, is -2. So that means this is -2. This is -2. This is -2, -2, -2, -2. When oxygen is in a peroxide, which looks like that, that would be hydrogen peroxide that you buy at like Walmart or wherever, put on your sores. That has a -1 charge. Okay, so in a peroxide, oxygen is -1. All right? So you can see that here, peroxide is a -1. There's also a superoxide, but I'm not going to say that for chemistry majors with Dr. Harris. But for the most part, again, this is general chemistry. Oxygen, -2, peroxide, -1. Okay? Hydrogen is always +1 unless it's bonded to a metal. All right? So hydrogen is always +1 unless it's bonded to a metal. So for example, sodium, so here hydrogen is +1. Oh, that's kind of cool. +1, +1, -2. Hey, water's a neutral molecule. Kind of cool, right? Over here, sodium hydride, and I'll tell you a little secret on why sodium now is negative. You can probably figure this out from this amazing thing called electronegativity. This is 0.9, this is 2.1. Which direction are the electrons going? To hydrogen, they're going that way. Oh, that causes hydrogen to be the negative and positive to be the sodium. So when hydrogen is bonded to a metal, it is -1. So in sodium hydride, hydrogen is -1. Okay? So there we go. Oxygen's always -2 unless it's a peroxide, it's -1. Hydrogen's always +1 unless it's with a metal, it's -1. Boom. Isn't that kind of fun? We've already memorized those rules. We're already working through those rules. But the rules keep on going. So let's go ahead and save that for, what is it? Is that the right time? What time is it? 2:04. Okay, yeah. I'll pick this up on the rest of these rules. We'll hit these on Friday, then we'll do our work. Sound good? Awesome. Exciting stuff.